Hello, this is Brian Washburn. I like to do a problem in Hamiltonian mechanics, and so I have a two-dimensional problem here. And what I want to do is I want to solve for the equations of motion for this problem, okay, using Hamiltonian mechanics instead of Lagrangian mechanics. So let's take a look at the problem. What I have is I have a cone, okay, and I have a mass m. That mass is it's constrained to move along the cone. So the thing can rotate in a circle, but has to be fixed to the cone. Okay, so it can't move. The cone is kind of a two-dimensional surface, and it can only move to the surface of the cone. Okay, it can't come off the cone. All right. So if I look at equation constraint, there's a relationship between rho and z, where z is equal to c times rho. That's the only equation constraint it has. Phi can be anything. Okay, so from this, it's naturally to use a a cylindrical coordinate system. All right. So what is my methodology for solving equations using Hamiltonian's method? Let me review that. Hold on. So my steps for solving a problem mechanics, Hamiltonian mechanics, is the following. I'm going to first find the Lagrangian. So I find the kinetic energy, potential energy, and the Lagrangian. And what's more importantly, I look at the degrees of freedom, and then I also look for any cyclic variables, because those are big conserved quantities. Second step is what I'm going to do is I'm going to define the generalized momentum for each degree of freedom. The third thing I'm going to do is calculate the Hamiltonian using that linear transformation. And then the fourth thing, once I have, and then, by the way, when I calculate the Hamiltonian, I want to make sure my Hamiltonian is in a function of generalized momentum and generalized positions only, and time maybe. In this case, it'll be a conservative system, so time will not explicitly be there. And then for each degree of freedom, I'm going to have two Hamilton equations of motion, so I'm going to use those for that. So this is, okay, so let's take a look at our problem again. So looking at our problem again, notice that this thing can move. There's one equation constraint. Okay, so again, I have, think about generalized, let's think about how many generalized coordinates I'm going to have. Well, I have, again, one mass. So the mass is going to be, so that one mass can move in 3 dimensions, but I have one equation constraint. So I expect two degrees of freedom, two generalized coordinates, and the generalized coordinates I'm going to pick are going to be rho and phi. Okay, so then my Lagrangian in general can be a function of rho dot phi dot. Okay, and my Hamiltonian in general can be a function of rho p sub rho phi p sub phi. Now what we're going to find out here is that L is going to be cyclic in phi because there's no torque acting on it. And so really what I'm going to find is my Lagrangian is going to be a function of rho dot and phi dot. Okay, now my Hamiltonian in the end is just going to be a function of rho and p sub rho. Okay. And so we're going to see that pop up. We're going to see that conserved quantity kind of pop up. Okay, so we're going to have a piece of phi in there, but that's going to be a conserved quantity. So basically, by doing this problem in Hamiltonian mechanics, I can reduce a one-dimensional problem down to a two-dimensional problem. That's two-dimensional problem down to a one-dimensional problem. Okay, so, but we need to work a little ways to get there. So what do we need to do next? Well, we need to come up with the Lagrangian. Okay, so let's write down the kinetic energy, potential energy, and then we can write down Lagrangian. T is going to be equal to, well, we've done this enough. It's going to be mass times rho dot squared plus rho squared. Again, this is just the velocity squared in cylindrical coordinate system. We've done this multiple times already. Okay, but that's what I have there. But my equation constraint from this guy here, z dot, is equal to c rho dot. Okay, so then I can write that as, well, 1/2 m rho dot squared plus rho v dot squared plus c squared z dot, sorry, rho dot squared. Okay, and so then that's my kinetic energy is 1/2 m, and then I'm going to get 1 plus c squared rho dot squared plus rho squared v dot squared. That's my kinetic energy. The potential energy is just going to be equal to mg z. XY plane is plane of zero, potential energy mgc rho. So the Lagrangian is equal to just those two things subtract each other. Oops, sorry. Get rid of that. Okay. Okay, so that's my Lagrangian. Now, before I go any further, let's look at the functionality of Lagrangian. As you can see here, the Lagrangian is a function of rho, rho dot, and phi. But the Lagrangian is not a function of phi, or sorry, maybe I said that wrong, but it's obvious. It's a function of rho, rho dot, and phi dot. But Lagrangian is not an explicit function of phi. That means p sub phi is a conserved quantity, and that's going to explicitly show up in the Hamiltonian. Okay, so let's find p sub phi. P sub phi is equal to partial L respect to phi dot. That's my definition, and that's going to give me m phi squared rho squared phi dot. Okay, and that's my constant. So now so we got all that stuff. Now let's calculate the Hamiltonian. Okay, so now I have my Lagrangian and I have my generalized momentum. Oh, by the way, I forgot another. So that's p sub phi. That's a constant. The thing I forgot to do was let's calculate the momentum associated with rho. So p sub rho is going to be equal to, so p sub rho, actually let me not do it there, let me do it on the side here. Okay, so p sub rho, a little bit. So p sub rho is equal to partial L respect to rho dot. And that's going to give me mass 1 plus c squared rho dot. Okay, so now I have my generalized momenta. Okay, now we have to get the Hamiltonian. And the Hamiltonian is going to be a function of, now, well, let's not write the functionality just yet, but let's just do the transformation. Okay. Now remember, I have to sum up over all generalized coordinates. So I have to write this as p sub rho, rho dot. That's from the definition of the Hamiltonian. And then I have p sub phi, phi dot, minus the Lagrangian. And Lagrangian is this. Okay. Okay. However, remember the Hamiltonian is not a function of any velocities, p dot, rho dot, and phi dot. I gotta get rid of them. Okay. The question is, how do I get rid of them? Well, what I'm going to do is, so again, this term here, that term there, that term there, and that term there needs to go away. So how I'm going to do that? Well, I'm going to use the definitions of the generalized momenta that I have here. So what I can say is that from I can say that rho dot is equal to P sub rho divided by m 1 plus c squared. Okay. And then I have phi dot. Phi dot is going to be equal to P sub phi divided by m rho squared. Now remember, this guy here, that P sub phi is a constant. So I'm going to take those two guys and put them into the Hamiltonian that I have above. So P sub rho times the quantity, P sub rho m 1 plus c squared plus P sub phi dot, which is P sub phi m rho squared, minus, and then I got 1/2 m phi squared. Then I had to put in rho squared. I had to put in this thing squared, m squared fourth, plus, and then this just last term is the same. So yes, so now I have everything. Now there's no more velocities in this equation, and I can write this thing down as, so you can see that this term here and this term here are basically the same, so that's going to give me P sub rho squared 2. Oh, I said that wrong. Did I forget a term? Yeah, I forgot a term. Okay, let me fix that up here. So notice what I did was I have this guy here, I have that guy there, and then, yeah, I forgot this term here. Sorry about that. So I said that was wrong. So let's go back a little bit. Okay, so what I forgot this term here. So let's write that at the end. So I have 1/2 here, m. Let's get this out of here. Then I have 1 plus c squared, and then I'm going to put in p. Then I'm going to put in rho dot squared. So that's P sub rho quantity squared divided by, and I'm going to get m squared plus 1 plus c squared constant there. Okay, so now let's go back and look. Now notice that this term here, so here what I can do is that one of these cancel out, one of these guys there, this mass cancels out with that guy there, and then what I'm going to show is that, well, what I see is that term there is basically, this is 1/2 of that. And then, by the way, I made another mistake from before. This is a minus sign from there. Okay, so then what that's going to give me from adding those two terms up, I'm going to get here P sub rho quantity squared m 1 plus c squared quantity, like that. Okay. Now, what I have is I have this term here, and then I have this term here. But notice that that cancels out to a 2 there. One of those masses cancels out. So then I have this minus that. That's going to give me P sub phi quantity squared m rho squared half. And by the way, I forgot the 2 for that. Okay, and then I get plus mgc rho. That's my Hamiltonian. Now, that makes sense. And the reason why it makes sense is, let's take a look at the terms. This term here is the potential energy of the system. this term here is the total kinetic energy. So this Hamiltonian looks like T plus U, which is the mechanical energy system. Okay, and I expect it to be the mechanical energy system because the Lagrangian and thus the Hamiltonian is not an explicit function of time. Okay. All right. So now let's get the Hamilton equations of motion. Now that's not so bad. Okay. So let's just do that under below. So we're going to write P dot. Sorry. So again, my first equation of motion. So remember, for each generalized coordinate, I'm going to have two Hamilton equations of motion. However, this thing here, P sub phi, is a constant. Okay, so that's going to again reduce the dimensionality of the problem. Let's show that. So I'm going to show here that P dot is equal to partial H respect to so rho dot is equal to partial H respect to P sub rho. There's only one P sub rho, okay, and that's going to give me equal to P sub rho M 1 plus C squared that. Okay, so that's one equation there. Then the second equation is we're going to look at P sub rho dot partial H respect to, or minus partial H respect to rho. There's two rows. Okay, there's a row in the denominator, row in the gravitational term. So P sub rho squared minus, the minus is cancel. So we're gonna get a minus, but a minus is cancel. M rho cubed minus mg that. So we got two equations of motion there. All right. Now that's for rho. Now for phi, we can say that phi dot is equal to partial H respect to P sub phi. Okay. Well, that just gives us this equation here, which is the angular momentum. Okay. And then the final thing is P sub phi dot is equal to partial H respect to minus partial H respect to phi. Well, that's equal to 0. Okay. So that's conservation angular momentum there. This is that P sub phi dot is equal to 0. That means that that's equal to 0. That means that P sub phi is a constant. All right. So now what we can do is we can rewrite those equations. So remember, this is a one-dimensional. It looks like a two-dimensional problem. Remember, I have 4 equations, 2 first-order differential equations for each generalized coordinate. But we can easily write this as a one-dimensional problem. And the way I can do that is I can recognize that, well, this is equal to a. So what I can do is writing the first equation. So let's rewrite the first equation in a second. So the first equation is just this. Okay, that's that. That's not a big deal. But then my second equation, actually we don't have to rewrite anything actually. Those are my equations of motion that need to be solved. That's it. We don't have to actually rewrite anything. And this is one dimension. So basically we solve, what is it, a one dimension we solve for? We solve for that. Then once we have that, then we're done. Because solving for this is easy. That's just equal to, well, we can just say it's equal to this, or actually we should rewrite it as like that. Okay, that's the solution for that. Okay, so then we need to solve these equations here. Now, one nice thing about this, so you say, well, how do we solve that? Well, it's not linear. So one way you can do it is you can use Runge-Kutta. Now the cool thing about this is actually a cool thing with Hamiltonian mechanics. Remember, if I want to solve an equation using Runge-Kutta, I have to rewrite a second order differential equation as two coupled first order differential equations. I kind of have it in that form already, so I can just stick these equations right into Runker-Kutta. If you don't like that, then what you can do is you can take P dot or rho dot, so then you can say that rho double dot is equal to P sub rho dot m1 plus c squared, and then you stick this into there, and then you get a second order differential equation, all in terms of rows that you can solve. Okay, so that's the problem. So again, to summarize, what we did was, our method for solving this type of problem is, we basically wrote down the Lagrangian. But in writing down the Lagrangian, we recognize that this particular problem is cyclic in phi, and so p sub phi is a constant. So then the Hamiltonian becomes basically one dimension, or it just has 1 degree of freedom, which is rho. Okay. And so in solving this problem, what we did is we wrote down the Lagrangian. Then what we did was we used this transformation to transform the Lagrangian, which is a function of rho dot, and phi dot, into a function, Hamiltonian function, which is a function of p sub rho, p sub phi, and rho dot. Okay. And then when we look at that, now, by the way, this Hamiltonian here, we could have guessed that Hamiltonian. Why? Well, because, I know we went through all the steps, but in the end, what we could have done was to say, hey, this system is a conservative system. It's conservative because Lagrangian is not an explicit function of time, so I'm just going to write down t plus u. And instead of writing it into rho dot and phi dot, I'm going to write it in terms of p sub rho, p sub phi. So you could have done that. That's actually the better way to do this than go through this whole process. Okay. Now you can only do that if it's conservative. If it's not conservative, then you have to use the transformation properly that I wrote right here for whatever Lagrangian you may have. Once I have the Hamiltonian, then I get for each degree of freedom, I get 2 first order differential equations. And again, because since angular momentum is conserved, I can rewrite that as this is basically one equation, and then I can solve that equation. Okay, so that's a method, the cone problem using Hamiltonian mechanics. By the way, any problem in Lagrangian mechanics you should know how to do in Hamiltonian mechanics. We'll talk to you later. Bye-bye.